Okay, I think that everybody in this room has worked with difficult systems, and I think also that you have also said this must be simpler. So in this talk, I'm going to talk what I have done in this system, in this particular system, to make it simpler. Okay. So the model is extremely simple. We have particles that are this is evolution. The particles that are these orange points. Here we have 10 points that are placed in this case in a regular position, but the position will be random. And they start with a random velocity. And as time evolves, they go, these point particles go with constant velocity until they meet. And when they meet, they merge. And the velocity of the merged particles will be the one that is compatible with the conservation of momentum. And when you have a merged particle, the merged particle behaves in the same way as the normal particle. So again, it can collide and merge, and always the mass will be the sum of the masses that are colliding. And as you can see, after some time, you will have a final configuration where there will be no more collisions. In this example, we have 3 final particles. So we are going to make 4 questions for these systems. One is, what is the mean and variance number of final particles? In this example, we obtain 3, but if we change the velocities, probably we'll have another number. So what is the mean average? But what is the mean number of final particles? But when the system has n particles. The other question is, what is the mass distribution of these final particles? As you see, this bottom particle has a mass of 3, the one on the middle is 6, and the top one 1, that has no collision. We want to say, yes? Yes, exactly, yeah. And we want to say something about the distribution of masses. Also, we want to ask if the exact number of final particles can be determined without evolving the system. In this case, if we evolve the system, we see that we have 3 particles. Now, if we don't evolve, but we know just the velocities, can we know how much particles do we have at the end? And the final question is how much energy is lost in this system. Okay. As you see, this is a system extremely simple, and the questions also. This can be part of a problem in first course of statistical mechanics, or even in physics 101. So hopefully the solution is not so predictable, I hope. So let's start. Some preliminary notation. We will have n particles. Y will be the position, y1, y2 are the initial positions. The leftmost particle will be the number 1, and the rightmost number n. And each one will have some velocity. Xn will be the number of particles at time t. But we are interested principally in the final number of particles, that is x tilde. Okay. And some notation, capital M will be the vector of masses of the final masses. M1 is the mass of the bottom particle, and mx tilde n, the one of the top one. Okay. So in this example, n is equal to 10. We start with 10 particles. At the end, we have x tilde equal 3, and the masses are 3, 6, and 1. So what are the hypotheses of the model? The hypotheses are the velocities B1, B2, Bn is a sequence of IID random variables. They are independent and identical distributed random variables with some density. They cannot be discrete. The velocities will be continuous, so we will not have ties. Particles will collide or not collide. And there is no hypothesis on the positions. Position can be any place. Any question here? Okay. So let's start with yes.
Calculating the mean several things.
Yes.
Those are for a fixed value of B1, B2, Bn.
No. B is the thing that changed. For a fixed value of B, we have only one final configuration.
By the velocity.
No, that's part of the results. That does not depend on the initial positions.
But the initial positions are also not. So
yes.
For the initial positions are
yes, both. Yes.
And the result is that the final state is independent of the middle dependence?
Not the final number of particles is independent of the positions, and as we will see, on the distribution of velocities. But of the positions, it's very clear. Let me show you this example. Let's put, yes.
Particles cannot be at the same position.
No, because that's the only thing. We need left, right, so we can think that particles are in random position given by a density. So you will not have in the same position. That's the only thing. So let's think we have the simplest model, two particles. Two particles may merge or not. So the final configuration is 2 or 1. The probability of having one final particle is that the velocity of the left is greater than on the right, so they collide. And this, as you see, is independent of the law of the probability law of the velocities and the positions, obviously, in the case n equal to. No, it's an open system. But this final, when we say, okay, we are going to study the number of final particles will go to infinity, but the number of final particles is well defined.
And you say that the final time is really the time is going to infinity, or you have that final time?
For me, it's okay. It's a good point. What is really dependent on position and velocity? The only thing that, as we will see, that is really dependent on position and velocities is this particular time. That for me is not important because I'm going to study the final configuration that doesn't matter when occurs. Okay. So what happens if we have 3 particles? Now if we have 3 particles, the final configuration can be 1, 2, or 3. It's free if you have the leftmost, the greatest velocity, the middle, and the smaller one here. And this happens with probability 1/6, independent of the distribution of velocities and independent of the positions. If you want to calculate the case equal to, it goes to 1/2 and
So the particles only move in one direction.
yes, no, yeah. When they are in opposite direction, they collide, and they merge, and you have.
When they go in the same direction.
Yes, yeah. This is one of the cases, for example. In order to have 2 particles, you need to have only one collision, and in this case, perhaps B1, that this particle that is here, is greater than this one, and they go in the same direction and they collide. I don't say that this must be to the other direction. Okay.
You consider the direction combination is negative.
Yeah, sure. So if we run simulations, not for n3, for greater values of n, we see that it is true that the positions are not relevant. This is, we can prove that. And the velocities, when you put an initial condition of velocities, you will have some number of final particles. But the point is, if now this B, that is the initial condition, I put a random initial condition, what will happen? And the point that I think it's interesting is that the final configuration does not depend on the law for the velocities. Okay, this is that it is distribution free. Let's say if we start with particles that have a normal distribution, we'll have a law for the final number of particles that is identical to if we start with another probability law for the velocities. Okay. So let's start with our first question. Our first question was, okay, what's the mean number of final particles? If we run simulations, you observe this behavior. As a function of n, this is in log x scale. We see that the mean number of final particles goes like log n plus a constant here, 0.5. And there is like some deviation for small values from 2 to 10, let's say. If we study the variance, you observe basically the same behavior. It goes like logarithm of n minus 1. But the point is, we want to find something analytically, and where is the difficult part? And the difficult part is how to compute these probabilities. You can imagine if you fix a number arbitrary n of particles and you want to know at the end what is the probability of obtaining k particles, it's difficult to compute that. Okay, up till here. So now we are going to introduce another model. And this other model will be much simpler. So this is the key here. The new model, look, this is the initial condition of the n particles. This is the initial condition of the n particles. It's exactly the same. But this model that is called non-physical, what happens? When particles collide, the velocity of the merged particle is the minimum velocity of the ones that are colliding. Okay, that's why it's called non-physical. So now, let me show an example. In this example, we have a final number here of 3 particles and here of 2 with this initial condition. I will talk about Z for the non-physical and X for the physical one. And now the obvious question, what is the relationship between both? Okay. And if we run simulations, we observe that the dots, and one is the physical and one is the non-physical system. We observe that the mean average of final particles is the same. If we compute the variance, it's the same. If we study the distribution for, let's say, we study a system that starts with 10,000 of particles, and we study the distribution, the probability of obtaining, the empirical probability of obtaining 11 final particles, we see that it's the same. So this system, and for small n, that the behavior was different from logarithm m, we have these results. First, note that they seem very similar. For n equal 2 and 3, we can obtain in both systems exact results. And one of the nice things is here, we are obtaining exact results. and here they are simulations. Okay. I'm going to talk about how to compute this, but I imagine that you can. Yes. Yes. For each n, we obtain exactly the same, even for small n. Let's say 10. For n equal 10, the mean number of final particles in the non-physical model is approximately 2.929, and this is 2.930. Yeah, so this confidence interval have this value. I think that 10,000. I'm not sure, but something like that. So. Yes, that's true. But I can choose the maximum velocity and it will be the same. So I will have always a bias to one direction or to other. That's true. Yeah, that's true. Yeah. Yeah, but as you see, the final configuration is the same. No. You see this figure. When they collide, the one that is the minimum velocity will win. So, yes.
In absolute value, or it's negative?
It's negative. Yeah, that's why if you see this figure, basically the two particles have negative velocity. So it's fair to say that at least the first two moments of the physical and non-physical models are the same. And I think that there is a stronger relationship that the distribution is the same. We check by Kolmogorov-Smirnov test, and we couldn't recheck the null hypothesis of equal distribution. But no matter, we are going to conjecture these two moments are equal. So now that we have this result, the non-physical model deserves to be studied. So, and this is much more simple. In this case, as you see, the only important thing is the order of the velocities. It doesn't matter if it's 100 meters per second or 10,000 meters per second. The important thing is it's the highest velocity, okay, or the smallest. So this will finish the story in a combinatorial problem. So in order to compute the final number of particles, we are going to introduce two functions. One that is a function for finding the place of the minimum of a sequence. We'll have numbers from 1 to 10, let's say, and where's the number 1? And if you have another sequence, where's the minimum of this? This function will say, okay, in the fourth coordinate is the minimum. And we are going to define a function that will cut sequences. If you see this figure, if I go from here to here, if I find this, then I cut and I study the following. That's a little the idea. I will show this example in order you to understand. When we start with 10 particles. They have certain velocities, and from this velocity, I say, okay, give me the order. And the order is the leftmost is in order 5. They are in the second order 8, 1. Okay. So I apply the function k that's over the sequence that finds where's the minimum. The minimum is at the position number 4, as you see. Number 1 is in the 4th position. And then I apply the cut function that it it have the sequence, and it cut the sequence and stay and remain the right part. And now I apply this sequence here, and it was the minimum of this sequence, and the minimum is here in the second position. Okay, and so on and so forth, until you find a sequence that you don't have a minimum because it's the null set. So we can say that the number of final particles is 4, and the size of each particle, of each final particle, will be 4, 2, 3, 1. If you see in this figure, oh, the same was the minimum here. So the size is 6. We continue what's the minimum, the last one. So the size, pardon, this is 7, the size will be 3. 7, 3. Okay? Any question? Okay, so basically we have a procedure to compute what is the final number of particles without evolving this non-physical model. We need to find what is the minimum k such that we find this empty set. Okay? So now, this is, if you have an initial configuration, you can know what it will be the final configuration. But we don't want a result for a particular initial condition. We want a result for the mean, so this initial condition must be random. But the initial condition random, it's easy because, yes.
No. This
K is the function that says let's see this example. S1, you see, S1 is not the empty set. S2 is not the empty set. S3 is not the empty set. S4 is the empty set. Okay, K is 4. If you continue from S to the empty set, you have an empty set. This is by definition. Okay, so now we want to, our main was to understand what is the mean and variance of the random variable set. So we need this sequence to be random. So the space of sequence is the space where we have all vectors of dimension n that we can rearrange, that we have n factorial possibilities. And from these n factorials, now, if we choose random one of these configurations of velocities, we obtain really now a random variable. It's okay? So what we want to do with that, we want to compute, for example, probabilities. So the probability of obtaining k final particles is the number of small omegas that verify that you have a final number of configuration equal k divided by the number of total possibilities. And the most important thing for us was how to compute the expected value. And the expected value can be computed as always, or much simpler, we can, this is a sum over n, and this is sum over n factorial. And we take all sequences and we compute the number of final particles, and then we make an average. Obviously, the space is very, very large because it's n factorial. That's why when I show here this table, I'm doing this, okay? This, let's say, 30,068 is the number of the sum of the numerator, okay? It's okay up till here? So now the point is, okay, this can be computed for small n because it goes like n factorial. Is there a way to compute any value n? How to calculate the mean value for any value n? And we have a result that says, yes, the mean value is the harmonic series. Okay? And the variance can be computed. It's like with a combinatorial argument can be proved that. Okay? And the harmonic series have a, for n large, we have a log n plus a constant. This is the Euler-Mascheroni constant that is 0.52. At the beginning, I said that was the empirical result says let's go like log n plus 0.5. And the variance is this. That is very similar to log n minus 1. Okay? So up till now, we have shown that if this is true, then as we have computed the mean number of final particles of the non-physical model, we are knowing the mean number of final particles of the physical model. Okay? Okay. So now, the other question was, can the exact number of final particles be determined without evolving the system? I mean, in the physical model. And there are some details, but I will try to show the idea. In the non-physical process, we define this function, this cut function, and this function that find the minimum. And in that way, we could compute the number of final particles. And we are going to say something similar. It's possible to calculate the mass and the final number of particles. And if you compare this with this, it says, okay, you have to find the minimum k, blah, blah, such that Rk is equal, Rk of the velocities, now velocities, not sequence, is this empty set, the same. What is R, we will discuss. But R is the simple thing, is the cut function. But here, this k tilde is the function that finds the minimum of the sequence. And here we have an m tilde that is another thing. But it's not so different, okay? So there is a very important result that perhaps for you is obvious, but for me at the beginning was surprising. That is key for the previous result. That is okay, take one of the final particles, whatever, this one. What is the velocity of this final particle? And the velocity is just the mean, the average velocity of the ones that compose it. Take any other, and it's the same. Okay? And this is true because the system is of identical particles. Okay? So any final particle will have a velocity that is the average of their neighbors, of the ones that compose it. Okay? And you know, if you want to try to understand what is at least the dynamics, if you have an average, you know, you have the central limit, the law of large numbers that says, okay, this will go to the, if you have a final particle with a huge mass, remember, the final particles are log n when we have n particles. So we will have very few final particles. And these few final particles will have a small velocity. So with this result that the final particles have a velocity that is the average of the one that compose, the function m, that is the important for understanding how much particles are in each, what is the mass of each of the final particles, is in this way. Let me show you this example. In this example, we have 9 particles. The one that is with the number 10 is artificial. You will see why. So basically, what you want to do is you want to find from all these, which is the value J, where I have to finish in order to have a velocity, a mean velocity of the merged particles in the left, smaller than all possible velocity that can be formed from the right. That can be 5 with 6, 5 with 6 and 7, 5 with 6, 7, 8. Okay, and when you find this J, you stop. Okay, you stop in 6. And now you again a cut function, and you study this in the same way. And in this way, you can find the final configuration without devolving the system. Okay. So let me show you an example. These now are really velocities. Okay. So see, the particle that is in the left has velocity 5.4, and the one that is immediately on the right is 2.1. So they will collide. But this goes like this, and this goes like this. So they will collide. Now, the average velocity of this is of the order of 3 point something. And 3 point something is smaller than 8.5, than 8.5 plus 1, 3 divided by 2, blah, blah. So you finish in 2, you see the sequence, and in the same way. Okay? No. No, yeah, in this example, yes, but yeah. So we have, now, if we have this initial velocity, we can find which is the number of final particles and what is the mass of each of the final particles, again, without devolving the system. Okay. The other question was, what is the mass distribution of these final particles? One thing is that Sn, that is the mass vector divided by n, okay, this goes up to 1, is a random vector of random lengths, because the number of final particles can be 10 or 12. So it's difficult to understand the distribution without condition to a particular length of this mass. So if we condition to some, we study this conditioning that the final number of particles is n, some value that I'm going to show, only the case where n is the expected value. Okay? If we study that, we observe this behavior. We observe that, first of all, the physical and the non-physical model, again, behaves in the same way, have the same distribution. And this cumulative probability on the right goes as log n, so the density is 1 over s. Okay? Seems to be. Any question? Okay. So, and finally, I want to tell you something about how much energy is lost in the system. It is clear that if we define L as the initial energy minus the final energy divided by the initial energy, when particles collide this way, the final energy will be almost 0, so L will be near 1, and if they collide in this way, will be L equal near 0, okay? But this is if we have only 2 particles. What happens if we have n particles? So if all are like frontal conditions will be close to 1, close to zero. But one important thing is that now the velocities are relevant. Why? Because these conditions can happen if the, or perhaps we have more collisions in this way if the distribution is asymmetrical. If all particles have positive velocity, and this, if they is symmetrical, this will have more or less. Okay, so in this case, it's the only case where that I studied that the distribution of velocities will be relevant, and the total number of collisions will be huge because it's the final number of particles is log n. So basically, the number of collisions is n. It's n minus z, but it's n. Okay, so exactly how large L is not evident. So I'm going to make an approximation of the energy lost and see what happens when we make this approximation. We know that at the beginning, the expected initial energy is just 1/2 nm times the expected b square. Okay, and at the end, we have much less particles, but we will have particles that have a huge mass. And what is the approximation? The one that's here. What this means that we will think that there are particles that are at the edge or the border that has practically no collisions. And the ones in the middle that are like trapped will have a lot of collisions. Okay, so this is, we write in this way the energy, and we say that the velocity of the edge basically is as no collision is there, and the velocity of the particles that are in the middle, on the center, we will say that basically, as we have shown, these particles have a velocity that is an average. So if you want to know its velocity, you know that the variance goes, if you have something that is an average, goes as the variance of the original thing that you are studying divided by the number of particles that you are averaging. So in this case, it's easy to see that the velocity of the central particles will be like that. So if you put that in the final energy, you can compute what is an approximation of the energy lost. Okay, and you see it's very clean. The expression goes like 1 minus the number of final particles divided by n minus 1 minus the final number of particles divided by n, and more important, this term appears. A term that has to be with the expected value of the velocity. If it's symmetrical, this will be 0. And it's a ratio of the expected velocity and the square velocity. Okay, so now we run simulations and see how it works. We are going to run one, and for large n, it's clear that this disappear, this disappear, and we have a very clean expression. Yes.
Sorry.
No, here we have only physical. We don't have non-physical. So we run simulations for the case where it is symmetrical, the velocity distribution. So in the case where this term will disappear, and I show here results. The points are the uniform distribution, the normal distribution that are not the same for small values of n. And this equation 16 is the approximation. Is this approximation? Okay. And as you can see, at least for the uniform and for the normal distribution, works very well. This means that for a system of 10 particles, the expected loss is 70% of the energy. And for large system, basically solved. And if we now study the case where the expected value is different from 0, in this case, we put just a very simple distribution that is the normal distribution, but not centered at 0. We center at 0.5, at 1, and at 2, with variance with equal the variance is 1. And we see again that the expressions works very well. And if for a system of 10,000 particles, if we change different distribution, not only normal and uniform, we obtain gamma, beta, blah, blah. We obtain that the theoretical and the empirical results are.
The results of the loss with let's say the area, because what matters for when you do tendency is that, as you said, that you have in opposite directions. Is there no way to relate with the area that is below, let's say, inconsiderable, and the area above, using, let's say,
I don't know, perhaps yes, but I understand that there is some relation, but how is this relation? I really don't know. So, to finish, we have presented a non-physical model that show that we have shown that have results that are statistical equivalent to the ones obtained for the physical model. So this is a question for this audience. We have seen similar things, no? That systems have statistical equivalent properties to other systems, but typically in a phase transition. And here we don't have any phase transition. So is it possible to think of that non-equilibrium processes can be categorized in some classes of models? Okay. At least we have shown that non-physical and physical in this particular example behaves the same way. And I think that some concept and outcomes presented here may be beneficial in understanding other equilibrium processes. In particular, we can think of an analogy with gravity. No? Here we have a system where particles, when they collide, they fuse. But this is really important if they fuse or if they are trapped. And you try to understand what is the distribution of the size of the galaxies. And that it's like analogous of the distribution of the size of the final particles. Obviously, this toy model is dimension 1, but perhaps an astrophysics system can think of other problems that might be interesting. And finally, there are some gaps on conjecture that might be interesting. As I told you, for example, the velocity that is independent of the velocity. I don't have a proof for that, but I know it's true. Not for the positions. Yes, we have a proof. And that's all. Thank you very much. And if someone is interested, this archive paper.
Questions? Well, there were a lot during the talk, but yes.
In which sense this is an out of equilibrium system?
We start with n particles, and they go to infinity, and we have a number of final. But if you have something that is diffusing, why this why you cannot make the same question? Why something that diffuses is not out of equilibrium?
I wouldn't say it is out of equilibrium.
Okay. And what do you think? Which would be the correct term for?
No, I'm hesitating to try to understand it. But in principle, you have a mechanical system
Yes.
in which you don't have any input of energy, maintain it in any particular state, so you just leave it to follow Newton's rules.
Yeah, that's true. But
So what is the non-equilibrium?
But there is no Boltzmann distribution of the final position.
yeah, no.
There is no temperature. It's a zero temperature system.
Um,
Yeah, the average square of velocity from is
This is a zero temperature system.
I think it's. I don't have an answer, but it's. I would love to know what would be the correct term, or what the correct title for this talk.
Okay, my other comment is that the question you pose at the end is interesting in the sense of what is a relevant variable and what is a non-relevant variable. But there are other or many other examples of physical systems which are not at a critical point and which they have irrelevant variables.
Mm-hmm. Yeah.
So I would not link that to critical phenomena.
Okay. Thank you.
Yes, and for me, it's like it's very critical that all the calculations are asymptotic in time. No, so time is going to infinity.
No, but, okay.
You don't pose the question of what is the number of particles at some intermediate times. At,
No,
let's say
because
time equal to 10.
No, because
So-
this depends on the velocity and the positions.
Exactly.
And
And I guess the two processes, the Z and X, will also differ in this at these intermediate times.
yeah, sure.
So did you, I'm just curious if you investigated with simulations or something, how they converge one to the other as time goes on or
No,
things like
because
that?
the point is, in this case, everything is dependent on the distribution. So I will not have any universal result. So that I don't say that it's not interesting, but will be very dependent on that.
Yeah, but for me, the interesting thing is to see how this dependence gets erased through time, you know, like you should have some tendency, you know, you have to have some term that is getting erased as time goes on.
Mm-hmm. Okay, thank you.
Yeah, well, good question because I mean, nice talk, but I miss a motivation.
The motivation.
I mean, can you maybe discuss with this?
Okay. The first motivation I think is if you believe that this analogy with gravitation is not something that is like, okay, this cannot be an analogy, then a one dimension, the toy model for the one-dimensional case is, I think, a good motivation, because the distribution of galaxies is something that astrophysicists people study, and it is not known. But pardon?
So particles are free.
Yes, and in after Big Bang, they are free also.
Well, there is an interaction, it's not here.
Yeah, but no, but I mean, you can think that galaxies, they are going to some velocity such that they will not attract. So this, you can obtain a final size or a final number of galaxies that it will be stationary.
Jesús,
and
¿querías
you
seguir?
study what is the mass of that.
¿Querías preguntar?
Ah.
No sé. He visto que levantabas la mano, pero no sabía si era porque querías preguntar o porque. Ah, sí, sí.
So thank you very much. I had another question regarding, I don't know if maybe I didn't catch it, but why do you think it's equivalent, the physical with the non-physical? Do you think there is a mapping to another kind of, description of an stochastic process that, bridges the gap? Because I mean, you're only comparing in the non-physical, for example, if it's bigger or not. So maybe I missed it.
Okay, the first thing is that they are equivalent in a statistical meaning, no? Because if you, in this particular configuration, this is 3 and this is 2. So there is no like argument to put one model, like, how to say it, but, I don't have an answer really to
Yeah,
that
that could
question.
be interesting to, see, let's say, if there's any other abstract process in
Yeah.
which after the statistical considerations, then you arrive at that, mathematical process, and that it can also open the gap to, extend into the 2D case to the.
Yeah, I think it's very interesting, your question, but I don't have any idea how to do that.
No, it was a follow-up comment on your question. That is, maybe in the statistical sense, some configuration that are not the same in one and in the physical, non-physical, like average, because they, no?
Average, we obtain the same average.
No, in the sense that if at the beginning there are some configuration that have not the same destiny in the physical and non-physical sense in the model, maybe given that you do a statistical comparison between the two, this configuration average up and you basically lose the difference between the physical and non-physical model.
I'm not sure, because the variance and the probability law is the same. So it's not that the mean is the same, but the variance, so that this part, this long tail with this long tail disappear. It's.
But there are very specific configurations that have
different...
No,
I understand, and I think that's a nice question to see, like bottom up, when you know the configuration that are different, to understand which were the sequences that generate that, and try to say something about that. I think that's a nice question. Yeah.
Okay, thank you.
Okay, thanks. One final question. Do you know what happens when you try with 2D systems? When you pass to one dimension more, what happens?
Okay, I think it's not obvious, because you have to define very well the things. In principle, you have to change a lot, because you have to like fix an interaction radius that must grow in some particular with time in some particular way, because if positions are not relevant, you can have all the masses very stretched. So I think it's not easy, but I think some ideas here will be useful. For example, the idea that the energy, you can separate both terms of the surface, that in dimension 1, 3 is very different from the center. I think this will be useful, and other things, but others will change a lot.
Okay. Yeah, I was asking because in random walks, the 2D is a critical dimension in which they don't ever return to a certain point. And so in one dimension, you still have some sort of possibility of going through all the places. In 2D, the things start to change. No? Okay.
I think the overall condition that if V1 is greater than V2, and that's when they're going, that's if you start from having something saying that it's just one condition to a spatial-temporal gap. So yeah.
Exactly.
that's very interesting.
Yes, yeah. But I think it's not obvious and you have to defender mucho esas hipótesis. I'm sorry.
Okay, if there is any other question, no? Well, let's thank then the speaker again.